Hey guys, this is Foster Ace, and in this video you are going to have a basic understanding about what standard template library is in C++ and how you can use standard template library to facilitate your programming skills and learning capabilities. So our main objective in this presentation is to understand what STL really is, what are its main benefits, why should you use STL, and how can you easily learn it in no time. And trust me in this, but STL is actually pretty easy to understand and learn once you get the basic idea about what STL is. But before we start, you should have some basic concepts about C++ like arrays or loops or conditions or structures or classes. And another thing that you should have is a minimalistic understanding about data structures like stacks or heaps or queues, or even if you know about hash tables and other stuffs, then they're of course going to come in your advantages because STL provides you with all these data structures that you can think of. And the third thing is you should know what the basic algorithms are. For example, you should know how to sort, or you should know how to search, or these kind of basic algorithms, because without learning these things directly, implementing these functions are going to affect your productivity at the end. So without further introduction, let's get started. What is STL? STL stands for Standard Template Library. It's basically a bunch of predefined templated classes and functions wrapped in some standard header files like vector that comes with your C++ standard header files provided by your compiler. So before we learn STL, we should understand what templates are, because STLs at the end of the day implement templates in their implementation. So if you have a better understanding of templates, then you will have a better understanding of STL. And one thing you have to remember is that whatever standard header files and standard functions that are provided by C++, they are wrapped under a namespace called std. So before you start writing anything, like you used to use std in front of C++, like std : C++, cout. Sorry, not C++, but cout. The same thing you have to append in front of all the functions and containers that are provided by STL. There is a little hack that you can use at the top of your code. Many of you already know that. That is, you can say using namespace std, and so you can easily call the functions without appending std : in front of the things provided by the STL libraries. Templates are like variables for data types. That means that templates can hold data types like int, character, or any classes like strings, or even the basic structures, whatever you can define as a type, like class or structs that are derived, or the basic types like int, character, float, double, and a variable that can represent these data types are usually defined by templates. But not necessarily a template is going to define a data type. It can also define a value, like a template can be a placeholder for an integer particular. So it depends on the case how you are using it. But to be honest with you, a template is like a placeholder for your data types. And another thing that you have to remember is that templates are not preprocessors. I mean that there are many preprocessors, like you have defined many macros in C++ or C. Templates are not like that. They are not preprocessed before your code is compiled. So you should know that. And the third thing is that the templates are supplied their types via these angle brackets. Here is an example of a templated function add that is supplied the data type int to specify that the values that are passed to this function are actually nothing but integers. And we will see an example, and I think this is a very simple example. We can see that we are first of all including iostream for using cout, and here we are defining, and here we are defining our templated function. So what does this function does? First of all, to make templates usable, you have to write template and then angle brackets. Then you can use type name or class, whatever you like, and then define the placeholder. In this case, my placeholder is my type, and I have defined a function called add that will return a variable of my type taking input of two variables of my type, that is a and b, and all it does is it adds the two variables. Now, why I am going to use templates and not defining int or character or anything? Because if I am going to write add for every single entity, like I am going to write add for strings, then I am going to write add for int, for float, and for characters, it's going to take a lot of time. And the use of templates are only to reduce these times and write one function and use them as many times as possible, as flexibly as possible. So keep this thing in mind, that templates are nothing but placeholders that can take anything like any value. For example, when I am calling add with integers, specifying that add is using integer, it's adding the integers and it's returning 30. But when I am calling add with float parameters, it's giving me a float result. Even when I'm calling add as char and I'm passing 2 here, it's actually understanding that 2 is here, is defined as a char, and then it's adding 2 to a and it's resulting c. And when I am adding two strings, of course they are being concatenated, not added. And this one function can handle all these cases because it's using templates in its core. So this is a basic understanding of templates. You have to remember two things. First of all, templates are defined using angle brackets, and templates can hold any kind of type in themselves. And this is the main key in using your STL libraries. So what are the benefits of using STL? First of all, STL provides you with quite standard and predefined implementations of data structures like stack, queue, linked list, hash map, fairly covering all the standard ones that one can use. And every classes or structures that you implement, they can hold those things easily, making your program flexible and make you write less code, as we saw in the previous example. The next thing is the second point, that is STL provides customizable algorithms that act upon these data types that are provided by STL, and they are very optimally arranged so that you can use those algorithms in different forms, in different situations, because they are quite hardly overloaded. And the third thing is efficient time complexity. The STL functions are battle tested over many programs in many years, so they are quite efficient in case of time complexity and space complexity. Let me give you an example and you will understand. So there is a function called std sort provided by the STL libraries, and all this does is it sorts a given sequence of elements. Now for this example, you have to understand that I am giving you a scenario here. Let's say you are about to sort 3 times in your program. One, you are going to sort some data in ascending order, and then you are going to sort some data in descending order, and then depending on some property of the data, you are going to sort it again. So you are ending up with 3 sort functions that are handling different conditions. And yeah, you have written a lot of code, of course, but let me complex this scenario a little bit. All these arrays are of different size. Now you know that a sort function that is capable of doing best performance in one kind of size is not capable of doing best performance in another kind of size. Now these all scenarios are kept in mind when writing the std sort function, and the std sort function is implemented as this. Like when the array size is too small, it's using insertion sort because that gives the best performance. But when the array size is large enough, it turns out to use quick sort. And you can say that merge sort is better, but in modern hardware it's seen that merge sort is less performant than quicksort. Quicksort is in fact faster in most of the CPUs right now. And the third thing is, when you have a very large data set, your quicksort is going to take a lot of space in allocating memory. And to handle this, your STD sort, then if it sees that the data size is very large, it converts into heap sort, making the memory usage minimal. So you can see that in every case of your size of your data, it always gives you a very good performance and giving you a time complexity roughly around big O of n log n. That is best for sorting. Now STL stands up on three main code pillars. One are STL containers, second are STL iterators, and the third are STL algorithms. We're going to see a diagram that explains what these things are and how they are used. Now, for first thing is STL containers. STL containers are placeholders that can hold data. These items are presenting data like you used to use array, and the STL works the same way, but it can arrange the data in different kinds of ways, like a stack arranges the data in first out order, a heap arranges the data creating a heap, and so on and so forth. Now these containers, they allow something called as iterators. What are iterators? Iterators are nothing but, you can think iterators as a kind of pointers that can give you access to the items, and the algorithms that STL containers have use these iterators from the container to act upon the data held by the container and give you an optimal result in obviously best time complexity and space complexity. So keep this diagram in mind. This is all that STL does, nothing more, nothing less, in short. So what are the containers provided by STL? Well, STL provides different kind of containers for different data types. For sequential containers, that means the containers that are like arrays, they are holding the data in memory in a sequential manner. We have vectors, decks, and lists. Lists are very likely double linked list that you have learned in your data structure classes. And decks are a better version of queues. And of course, vectors are dynamically allocatable arrays that can easily be allocated using lists, using contiguous block of memory. But the catch is that whenever the allocated memory that you have allocated for the size of the data, let's say you have 4 datas and your max size is 8, when the data reaches 9, the max size is doubled, and then whole data is copied to another contiguous block of memory, giving you a consistent performance. That is what basically vector does. And these three things, as they hold the data sequentially, they fall under the category of sequential containers. The next thing are the associative containers. The associative containers doesn't hold the data sequentially and doesn't understand the indexing of the data, but the associative containers, they are there for holding the data and giving you the data in a very fast manner and having an associative relation between the data. Now, as we have seen that the vector is a dynamic array allowing random access to modification of elements just like normal arrays. However, insertion and deletion are allowed only from back of the container. And probably you are going to use vectors a lot because the insertion and deletion time at the back of the vector is order of n, but also vector gives you random access like arrays, so you can use indexes that you used to use in arrays. Now lists, they are bidirectional linked lists that I already told you. And the next thing are the sets and multisets. They are basically the kind of sets that you have read in mathematics. They hold that data in an associative order. And next we have maps and multimaps. Maps are hash tables with unique keys for unique values, and multimaps are associative arrays that have unique keys for many values. They are like hash tables. Okay, if you have learned about hash table, then you will understand that getting the data back is very faster from a map than a vector or anything, because whenever you are traversing the data and finding that data, you are taking a big O of n times. That means when you have a number of elements you are searching for n times in order to get the data. But in case of map, it takes a order of 1 time because it has a predefined function that runs and that immediately gets you to the data. And the third one is the derived containers, that are the stacks, queues, and priority queues. You already have learned about these things, so I'm not going to waste much time. But basically, a stack is a FIFO, not FIFO, but a stack is a LIFO. That means the last item to get in is going to be the first item to get out. A queue is a FIFO. The first item to get in is a first item to get out. But you can also push the items in the front and the back, both sides, because they have the functions called push front and push back in case of queue. And they also have the same functions of the priority key. Now, next thing is iterators. What are iterators? Iterators are like pointers. You have seen that an array is like a pointer, and so whenever you are accessing an array with an index, you are just accessing the pointer with something plus. Like I have an array and it has the third element. When I am asking the third element of an array, I am actually doing something like this. The main pointer to the array plus 3. I am increasing the pointer to 3 more data locations according to the contents of the array and getting the third element. In case of 3, although it gets you the fourth element, but I guess you have understood the idea. The iterators are like same. They are just giving you an handle to the data inside the container. And to get a iterator from a particular container, you just say the container name, then colon colon, and then the iterator. For vector, you will say vector colon colon iterator, and then you will define an iterator like it, and you will act with that iterator. Now, all the containers that are provided by STL, they give you two kinds of iterators to start with. First is the begin, that refers to the first element or the starting of the data structure, and the end, that refers to the last element or the ending of the data structure. So you can use these iterators, we will see in future programs, in order to access the data very fast, look through the data very fast, that is traverse through the data very fast, rather than your traditional ways. In most of the cases where you need to know what all the contents are, even if it's a set or a hash table or a multi-map or a queue. Now, the third thing and the most important thing are the algorithms of STLs. They act upon these data and they give us optimal solutions for that data so that our code gets absolutely reduced. Now, all the algorithms that are provided by STLs fall under two header files. One is algorithm and another is numeric. We can roughly divide the algorithms provided by STL into 4 parts. One are non-mutating algorithms, one is mutating algorithm, one is relational algorithms that define the relation between two sets or something like that, and then there are numeric algorithms for numeric computation. Now, I'm not going to give you example of all the algorithms because there are probably 100 plus algorithms in STL library, but I will give you a rough idea about what kind of algorithms you are going to get in STL, so that you can search them in Google or any other kind of media, and then you will find the signature of the functions and you can use them. So the first thing that we are going to understand are non-mutating algorithms. Non-mutating algorithm means that it's not going to hamper or it's not going to alter the data that are present in the container. Such algorithms are for each. For each is perhaps the most used algorithm by other programmers from STL. This one is going to be used a lot by you when you are going to start STL, because it allows you to apply an operation or a function on a set of data. The function might be anything, and it will run through the set of data traversing through each element. And of course, all these functions, they have multiple overloads to cover all the scenarios that you can have. The next one is find. Find finds the first occurrence of the value returned by a sequence. Now, one thing you have to keep in mind that these algorithms, they are not absolutely supposed to work on the entire container. Suppose you want to work on the part of the container. All these algorithms, most of them are taking two parameters at first. One is the starting to the data and one is the ending to the data. So these parameters are going to be placed there, and then the other parameters are according to the function. and these pointers, you can pass the begin and end in order to traverse or active the algorithm in the whole data structure. But you can also use small section, small portion of the container. You want to find the data in the first few elements, so you just give the iterators bounding those few elements, and then it will only work on those elements, and that will give you a more confidence or a more productivity in your code. The next thing is find actually helps you in finding an element of first occurrence in data. The equal checks if two ranges are same. Suppose you have given a first range are two sets of iterators, a begin and an end to a data, and the second sets of iterator for another data structure, and equal compares these two data structures to understand whether the data contents are actually same. The next one is count. Suppose you want to find the count of a value inside a range, and this is where count comes into play. It gives the number of the elements that are present and in that sequence and are matching to that data. Count if takes a condition and gives the number of the elements that match to that condition. Of course, I think you understand what find if does. Rather than finding a value, it finds upon a condition, and find in, where find finds the first occurrence, find in finds the last occurrence. So, and other few summaries search, where find finds a single element, search gives you a sequence matching all the elements that are present in your data or your query. Search n gives the first n elements that are present in your data that matches your query. Binary search gives you a better searching time, and it returns mostly all the elements that are matching to that particular function. And mismatch matches the two data structure in order to understand where the first data mismatches or the first data that is not matching occurs. Suppose a data structure is 1 2 3 4 5, another data structure is 1 2 3 6 7. So here they are mismatching, and it will give you an iterator to this position, so you understand that, oh, the fourth position of my data is actually mismatching, and you can work upon them depending on that. And adjacent finds two values that are adjacent but same, and also they are very much modifiable to your needs or your satisfactory conditions. Now, some of the mutating algorithms that we find in STLs are sort, that sorts the data. We have already discussed about that. Stable sort for stably sorting the data, and partial sort for partially sorting the data. You will see the implementation of these functions as we go along the series, but you can also Google these names and you will find the definition and how to use them in many C++ referencing websites. Copy creates a copy of a data sequence, and copy backward makes a copy of the data sequence, but it does it backwards. And all these things, they take two iterators pointing to the first element and the last element between which you want to sort or you want to copy. Fills a data structure with a value. Suppose you have a data structure filled with garbage values and you want to fill all the values with a certain value, so you can use fill. Like you want to initialize every value to 0, in that case you will be using fill. Now if you want to initialize only a few values like first 3, then you are going to use fill n. Generates the values depending on a condition, and it fills the data structure. Now iterate swap or swap, iterate swap particularly gets two iterators and swap the contents of the iterators. Swap the same way, it gets the two locations or the values and it swaps them together. Swap ranges can swap entire ranges of data. Like I have a range of data and I have another range of data. It will take this range here and this range here. So it's very handy. And random shuffles all the data between a given sequence. Like I have this sequence, it will become something like 1 3 2 0 or something like that using random shuffle. Now remove is used to remove a data, even like stack, where you are not supposed to get the data out from a middle. You can use this function and it will remove that element and then slide these elements backwards, so you finally will end up with something like this. And yeah, it's quite handy in order of mutating those data structure that are not supposed to be mutated in certain way. Remove if takes a condition and depending on the condition removes the thing, and remove takes a value and removes that value. Remove copy removes the value but also makes a copy, and remove copy if is self-explanatory. Now replaces a range of data, and merges two data structures into a one single data structure, whatever it might be. Even it can be a simple array, and all these data structures will work on that array because arrays have that thing built in, that is your what they say. And because arrays also have can act like pointers, and iterators are like pointers, so they all act on your standard C++ array also. And there is in place merge that merges two consecutive datas, and for these functions to work, your two arrays should be in order, like when you used merge sort. This is the same kind of merge function. And there is a make heap function that takes a certain amount of data and then makes a heap out of that data. And sort heap sorts a data structure thinking that it's a heap. Now there are some set operations also, like you have two sets, you want to perform set union on those sets. Like I have a set A and a set B, and I want to merge them together, so I will be using union. Or includes finds the particular value that is present in the set, or set intersection to find only the intersecting part of these two things, or set difference to get a particular difference, or symmetrical set difference for both the differences. These are pretty self-explanatory if you have learned about sets. And there are other algorithms like relational algorithms, like equal or lexicographical compare to compare two things lexicographically, or mean or max to get the maximum value or the minimum value from a certain range or sequence. And you have to keep in mind that all these functions, they are actually very much customizable and modifiable according to your need. In most of the cases, you can also pass a function, a pointer to a function or a lambda function to these functions, and you can tell these functions, oh, to sort like this. Like in the first example, when I asked you that you have to write 4 implementations of sort, you can just change the conditions of the sort function and they will act differently, although they are calling the same function. And there are some numerical algorithms like accumulate to accumulate the values, adjacent difference, you know what does that mean, inner product to find all the products, and partial sum to define partial sums. They are not very much used, but yeah, they are there. And there are also many other algorithms that I'm not covering here because I think that they're not that much important, and that whenever you need those things, you will learn those things once you get a hang of STL. So to say basically, in a summary, STL composes of 3 things. First are the containers, which gives iterators, and there are algorithms those algorithms act on these iterators, on these containers, to produce some value or some result. And these containers may not be containers, they also can be in an array, and the algorithms, they still can act on array because they will think these arrays as iterators. So though I have not mentioned all the necessary algorithms that are covered by STL, I think these are fairly enough. And more of all, you will not be able to remember all these algorithms, right? But you know what, when you find a problem next time and you can think, oh, this function, this algorithm, they are provided by STL, so I can use those things in order to facilitate my program, and I have to think less about doing these tasks. They will be automatically done, and I can focus on doing the more serious tasks. And that's why STL is there to help you write your code faster and effectively. So in the next videos, we will probably start with vector or something like that, and we will try to understand all these things that I have told you one after another, and they are very symmetrical in nature with one another. So once you understand one data structure and one container, or once you understand how one algorithm work, you will mostly get a rough idea about how you can use other algorithms or other containers. So trust me about this, they are very easy to understand once you keep this simple idea in your mind. So till next time, peace.